All right, so we'll talk about something related to buoyancy, and let me remind you of, so this is something we learned last time. An object will, where did my, where did my, I can't find my, how do I find my, all right. So what we saw was, where do I find my tools? Shoot. Anybody know how to find my tools? I need to find my toolbar. I can't find my toolbar.
In the corner, it says you're on the read only setting.
I'm sorry?
In the left-hand corner, the read only.
Mm-hmm.
Maybe if you change that, it'll let you.
Oh, there you go. Thank you. All right. So, so we learned the following. An object will sink if the substance density is greater than the density of the liquid. Okay. An object will float if its density is equal to the density of the liquid. Okay, so the reason we're talking about this is we'll talk about fish and animals that live in marine environments. So an object will float if its density is equal to the density of the liquid. And so it'll hover, it will neither sink nor float. And an object will float, will rise up to the surface if the object's density is less than the density of liquid. All right. So if you're a fish, if your density is higher than the density of water, you have to constantly spend energy to not sink. If you float, you don't want to float, you'll come above water and you have trouble breathing. So if your density is less than the density of liquid, you'd rise to the surface and you have to constantly spend energy to be underwater. Okay. So if you're a fish, what you're trying to do is you're trying to match your density to the density of the liquid. Okay. And so we'll talk about that. Okay. All right, so here is the first diagram we'll look at. All right, as an animal, what you do is you always you store extra energy for a rainy day. Okay. I mean, now we don't have to worry about that, but most animals, you don't know where your next meal is coming from, so you always have an extra store of energy. Okay. Now, if you have this extra store of energy, you have to carry it around all the time. It's like you're carrying your bank balance. So what is the most efficient way of carrying this extra store of energy? Look at this. Fats, this is kilojoules per gram. We carry our extra store in fat because that's the best bang for the buck. You get the most energy per pound. Okay, and so that's why that's almost 2.5 times the energy storage capacity of proteins and carbohydrates. So we store the extra energy in fat. Except that the problem with this is if you live in a watery environment, there's a problem with this. The density of fat is less than the density of water. So if you were 100% fat, you'd rise to the surface. Okay? So we'll keep that in mind. Okay? So we carry our store of energy in fat because it has the most energy per pound. Okay? So of the different body components, only fat has a density lower than water. Every other body component has a density greater than water. So if you're made only of muscle and bone, you would sink to the bottom. If you were made only of fat, you would rise to the top. Okay. So an average college student is about 20% fat. And our typical density is 1,050 kg per meter cube. The density of fresh water is 1,000 kg per meter cube. So the density of fresh water is 1,000 kg per meter cube. Okay, so if you were swimming in a freshwater lake and you did nothing, you would sink to the bottom. So to remain on the surface, you got to constantly spend energy. Okay, so by the way, so if you take a deep breath, you fill your lungs with air, and you reduce your average density, and you would reduce your density to 990 kg per meter cube, which would be less than the density of water, and you would float. Okay. Look at this guy. So manatees live in fresh water. Okay. So now, if you want to just hang out and not spend energy, what is it that you want to do? You want to match your density to the density of water. Okay. Too much fat would make them less dense than water. Okay. Which would increase the energy needed to die, and hover and so on. So these manatees cannot have too much fat. A typical body fat percentage for a manatee is 7%. Look at that. Compare that to 20% for me. It's 7%, comparable to an elite human athlete. Okay. This guy doesn't look like an elite human athlete, but that's his body fat percentage is 7%. Here's another amazing thing about manatees. So when you breathe in and out, what you're doing is you're only expelling 10% of the air in your lungs. Okay. A manatee can exchange about 90% of the air in their lungs, okay, compared to only 10% in the human. This high efficiency allows them to be submerged in up to 20 minutes when resting. So if you're swimming, then you would need to come up for air more often. But if you're just resting, you can go underwater for 20 minutes. Okay? That's because you have each breath you're getting almost 100% fresh air. Okay? Now here's the lungs of manatees. The lungs are long and they're right below their backbones. Okay? And here's a side view of the lungs. So there's the lung. It has two chambers. Okay? And this chamber goes all the way to the back. Okay? Manatee lungs are flattened, elongated, and run horizontally along their back, along the entire length of the body. And this is by design. So let's see what they can do with this. See, manatees can adjust the amount of air in their lungs to achieve neutral buoyancy. What does that mean, neutral buoyancy? Yes, same density as the water. So they can hang out underwater without spending any energy. Okay? You don't have to spend energy to rise up or fall down. Okay? So that's neutral buoyancy. They can also move air from one lung to another. If they want to roll this way, what you do is you move air from here to there, And this has more air, this becomes buoyant, this has an upward force, and you can roll that way. You want to roll this way, you move air from here to there. Okay? So from lung to roll, and from top to bottom. So if you move air here, then you can rise up. If you move here, air here, then you can dive. Okay? So, and they can move air from top of the lungs to the bottom to tip forward for a dive. They can also control the air in each lung separately. They can breathe so that they're getting in air only on this lung, or they can breathe air into this lung. Okay? So each lung separately to precisely adjust their position and trim. Okay? So they can, they have a lot of control underwater. Okay? All fish have swim bladders to control buoyancy. Okay? The body of a typical fish is like yours. The average density is 1,050 kg per meter cube, more dense than water. Okay, so if that was the average density, they would constantly sink, and to hover in water, they would have to constantly spend energy, and that's not a good strategy. It's it's like if you're sitting, you don't have to spend energy to just sit. Okay? So you have to spend energy to move and stuff like that. So this is greater than the density of water. So the fish would sink. They would need to expend energy to stay at the same depth. So all fish have structures. All fish have swim bladder. A gas-filled sac inside the body. They can control the volume of gas. So there's this swim bladder, and they can control the amount of air in the swim bladder. So you can control your buoyancy. So what would you do if you want to dive for food, if you want to go to the floor for food? What's the first thing you would do? Reduce the amount of air there so you can go dive to the floor easier. Okay? And if you want to rise, then you would increase the amount of air. Okay? So the fish controls the volume of gas in the swim bladder and thereby adjust its average density. Okay? For ocean fish, the swim bladder takes up 1 to 3% of the volume, okay, of their body. And for freshwater, it's more 5 to 7%. Okay. So why is the freshwater fish swim bladder greater? I'm sorry? No salt. Yeah, ocean water has a density of about 10 to 30 kg per meter cube. Okay, so the density of ocean water is close to the density of the fish, and so all you need is a small swim bladder to adjust your density. Okay, if you wanted to go to neutral buoyancy. All right. All right. So here's an interesting problem that you might have encountered before. Okay. So here's a glass full of water, and then you have several ice cubes in the glass. Okay. So the question is, when the ice melts, will water overflow? What will happen? Okay, so here's you need to recall Archimedes' principle. Okay, the weight of this ice, the reason it's floating is, the weight of this ice is being balanced by the buoyant force. Okay? And what is the buoyant force? So the weight of this ice is equal to the buoyant force, and the buoyant force is equal to the weight of this much water, the water that was displaced. Okay, so when the ice melts, its weight hasn't changed. It becomes equal to water, and so when it melts, its volume will equal this much. Okay, so the water won't overflow. Okay. So it'll stay the same. All right, now we'll talk about terminal speed. Terminal speed is, let's say you're a skydiver and you jump off a plane. That's the fastest you're falling. Okay, so if you fall spread eagle like this, for instance, your terminal speed is about 120 miles per hour. And if you fall in a dive position, then your terminal speed is about 180 miles per hour. Okay. By the way, I don't know if you know this, but DeLand is the skydive capital of the world. Okay, so this is where most of the skydiving happens in the world. Let's say a lot of skydiving happens in the world. Okay. Now, if you fall in a liquid, your terminal speed is much, much smaller. Okay. And here's why. So terminal speed, when you're going at terminal speed, that's you're not accelerating. Here are the forces on you. This is the drag force. The drag force is due to the liquid. This is the buoyant force, and this is your weight. Okay, so when you're going at terminal speed, these two forces add up to equal to that. Okay? And that's why you're not accelerating. So when you first start off, your weight is greater than your buoyant force, and so you're accelerating downwards, and this force starts getting larger, and eventually these two equal that. Okay, so you reach terminal velocity. When you're going at terminal speed, the drag force at terminal speed, this force is equal to weight minus that. Okay, this plus this is equal to that, so this force is equal to this minus that. So your drag force at terminal speed is your weight minus the buoyant force. And anyway, so this can be written as the density of the object minus the density of the fluid times the volume of the object times gravity. All right, for most objects, the density of objects is just a little greater than the density of the fluid. So this term is small. So that means the terminal speed is small. Okay, so if you're falling in a fluid, the terminal speed is very small. Okay, it's nowhere near these guys. Okay, and we'll talk about this. So the terminal speed, I'll show you a calculation for phytoplanktons. Okay, and so that'll important. So for an object that is submerged, the volume of the displaced fluid is equal to the volume of the object. Okay. There's often little difference between the densities of the object and the liquid it is falling in. So the terminal speed is much less than the speed in air. Okay. So the terminal speed will be small. All right, so there are two kinds of expression for the drag force. Okay. For large objects, so the drag force depends on, if you look at one of the previous chapters, there are two forces, inertial forces, okay, and then viscous forces in the liquid. Okay, inertial forces are if you're a large object, you have to move away the fluid, and that's an inertial force. So that's the predominant force. And if you're tiny, the liquid molecules sticking to your body, those are the main forces. Okay, so if you're tiny, viscous forces are important, and if you're large, inertial forces are important. Okay, so when inertial forces are important, when this is important, that's the drag force. Your drag force depends on your speed squared. And when viscous forces are important, then the drag forces depend on the speed. Okay? So this is the expression when viscous forces are important. Okay. And again, you don't have to remember any of these expressions. This is when inertial forces are important. Okay. And so as a rough rule of thumb, objects smaller than about 100 micrometer fall in water with viscous drags. So for microorganisms in the ocean, this drag force is what is relevant. Okay? While objects larger than a few millimeter experience inertial drag. Yeah. All right, so here are coccolithospores. So these are microorganisms. These are phytoplanktons in the ocean, and they are a major contributor to the sediment. Okay, so this eventually becomes oil and stuff like that. Okay, they fall to the ocean floor and become sediments. Okay, these phytoplanktons, where do we get all our energy from? Where does the planet get all its energy from? Sun. Okay, what traps sunlight? So you and I are not going and catching sunlight like that, are we? So something is catching the sunlight for us. Plants, we have photosynthesis, that's the first, I guess, trees and plants. And these guys are trapping half the energy, phytoplanktons. Okay? So we got to thank these guys for, that's the bottom at the bottom of our energy chain. Yeah. These guys trap half the energy. Other animals eat these guys and so on and so forth. I guess. So, all right, so what we'll see, so these guys are tiny, and then when they die, they eventually fall to the ocean floor. Okay, so this problem tells you, will show you how long it takes for them to fall to the ocean floor. The average depth of the ocean floor is about 4 kilometers. 4 kilometers is from here to US 1. That's the average depth of the ocean floor. Okay. So these guys are trapping sunlight. So these guys live near the surface of the ocean. Okay. And when they die, they have to fall 4 kilometers. Okay. And of course, they're going at terminal speed. Okay. So this problem goes through the calculation. Okay. So they're 30 micrometers in diameter. And again, you don't have to know the details, but you just have to have a sense for the answers. That's their diameter. They had to fall 4 kilometers when they die to the sediment. Okay. And their mass is 24 nanograms. Okay. So this calculates the density of these guys. The density is mass divided by volume. Okay, so this divided by the volume. You can calculate the volume from the diameter. So density is 1700 kg per meter cube. So the density of these guys is that. And the density of the ocean water is, the fluid therein is about 1030 kg per meter cube. Okay? So their density is greater than that, so they'll sink, obviously. Okay? And the drag force is equal to that difference. Okay? And these guys are small, the drag force is that term, is that formula. Okay? So the drag force is mainly a viscous force. That's the drag force. Okay? And so using that, you can calculate the terminal speed, and the terminal speed works out to 0.2 millimeters a second. Okay, so these guys, the phytoplankton, when this fall, 0.2, it takes them 5 seconds to drop 1 millimeter, 50 seconds, a minute to drop 1 centimeter. It takes them a minute to fall 1 centimeter. Okay, so they're falling that slowly, and they got to go from here to US 1. Okay, so those guys, after they die, they take about 240 days, almost a year, to get to the floor, to the ocean floor. Okay, but nobody's in a hurry. Okay, so these guys that are trapping half our energy, okay, after they die, they end up on this ocean floor, become sediment. And even then, after that, over millions of years, they turn into oil. So they're always helping us. Okay? All right, now we'll talk about a different topic, surface tension. Okay, water molecules attract each other fairly strongly, and this is via hydrogen bond. Okay, so if you're a water molecule inside, so if you're a water molecule inside, this water molecule is pulling you on that side. This water molecule is pulling like that. Okay, so as long as you're surrounded, then the net force on you is 0. So for all water molecules inside, the net force on them is 0. Yeah? But let's look at a water molecule on the surface. This guy is pulling him that way. This guy is pulling him that way. This guy is pulling him that way. There's nobody pulling him in that direction. So if you're a water molecule on the surface, there's a net force on you downwards. Okay. Now, so why is he there? Well, for any given volume, you have to have a surface. Okay. So, and for a given volume, what is the? So it costs you energy to be on the surface. So for a given volume, what is the smallest surface that you can have? A sphere. Okay, so if you have a small drop of water, it is always spherical. That's because that way you have the minimum number of molecules on the surface. Okay, so it costs you. So if you're a small drop, you'll be spherical. If you were like that, there's a larger surface area and it costs you more energy to have that surface. Okay, so as you get larger and larger, then your center of mass is higher, and then you are spending gravitational potential energy. So if you become a big drop, then you flatten out. Okay, but if you're a small drop, then you want to be spherical. Okay, so that's because of the surface tension. Okay, so again, what you want to remember is if you're a molecule on the surface of a liquid, the net force on you is downwards. Okay, and so the surface is under tension. It's like a stretched rubber sheet. Okay. So surface tension is caused by the cohesive forces between liquid molecules. That is, the attractive forces between liquid molecules. Okay. In water, the surface tension is a result of the strong hydrogen bond between molecules. Okay, so here's a water molecule. This is the hydrogen bond. So here's a water molecule, oxygen and 2 hydrogen. And what happens is in a water molecule, the oxygen is greedy for electrons. So it attracts the electrons stronger, so this is, the hydrogen atom is more positive, and this positive hydrogen atom attracts this negative oxygen atom. Okay, so this is the hydrogen bond, and this is fairly strong. Okay, so the surface tension is fairly high for water molecule because of the strong attraction. Okay. Hydrogen bonding can occur between separate molecules or within, so hydrogen bonding can occur between separate molecules or or different parts of the same molecule. So for instance, in your DNA molecule, which is a spiral like that, these branches are bound by hydrogen bonds. Okay, so there's a force between hydrogen bonds. So you can have hydrogen bond between different molecules or different parts of the same molecule. Okay. So hydrogen bond can occur between separate molecules or within different parts of the same molecule. Its strength varies considerably depending on geometry, environment, and donor-acceptor pair. And it typically ranges from 1 to 40 kilocalories per mole. So this is just giving you the strength of this hydrogen bond. To break these bonds, to pull them apart, it costs you about 40 kilocalories, about 20 kilocalories per mole. That's what that is saying. Okay. Hydrogen bonds are stronger than van der Waals interaction, but weaker than covalent or ionic bonds. We saw van der Waals bonds when we were talking about geckos. So if you look back to your earlier notes, you'll see that. Okay. All right, so surface tension arises because of cohesive forces between molecules. Okay. So here's how you can measure surface tension. So you can take a liquid and remember these molecules of the liquid are being pulled by those molecules. Okay, so to pull all these molecules, you have to apply a force. Yeah. All right, so shown is this experiment in which a liquid film such as soapy water is stretched between this contraption. A pulling force is needed simply to hold the wire. So you need to have a force to hold the wire. If you let go of the force, the liquid will snap this wire back. Okay, and so you use this contraption to measure the surface tension. The liquid pulls on the wire with a tension-like force, rather like a stretch spring. All right, so the tension, so surface tension is actually force per unit length. So longer this wire is, the greater the water will pull it back with. Okay, so the force that you're pulling with is tension. Okay, so surface tension is defined as this tension divided by the length of this surface. Okay, tension divided by the length. Okay. So the actual tension and this tension is equal to the force you applied. So that's how you measure this tension. Okay. So the actual tension of the surface is distributed across the line of contact, okay, and its units are T over L. Okay. So anyway, if the molecules attract each other strongly, if the cohesive forces, that is the force between these molecules, are great, then this surface tension will be great. Okay. All right. So because of the surface tension, because the water surface is like a stretched rubber sheet, that's why stuff like this can happen. You can have insects walking on water. Okay. So bubbles and it's also going to be important for how we breathe and stuff like that, and we'll talk about that in a second. Okay, so bubbles and water droplets assume a spherical shape. Insects walk on water, and liquids rise in a capillary tube. So these are some of the phenomena that happen, and these are all important in the biological world. These are manifestations of surface tension. Okay. Many biological processes, from the functioning of alveoli in the lungs to the extraction of water in soil by root, are governed by surface tension. Okay, so we'll talk about the capillary effect in a second, and the water rising in the soil to the roots is a capillary effect. When you use those paper towels and the paper towel absorbs all the water from a wet spot, that's a capillary effect. Okay. And so we'll look at all of them. Okay. So let's see how this guy walks in water. How come he doesn't falls through? Okay. So water striders, these guys are water striders, are known for their ability to walk on water. The feet of a strider are hydrophobic. Okay. So the molecules on the feet, they are not attracted to water. Okay. So, and they're hydrophobic due to thousands of microscopic hairs that enable the feet to push the water down into a dimple without breaking the surface. Okay, so the upward component of the surface tension around the curved dimple then support the weight of the strider. Okay, so here's an example. So have you guys seen a needle being floated on the surface of water? Yeah. So you can take a needle, and if you carefully place it on the surface of water, you want to use a tweezer without breaking the surface, you can float needles on the surface of water. Okay. And so here's a needle floating on water, and here's what happens. So this surface of the water bends like that, and the tension in the water, the surface tension, is holding up the needle. There's the weight of the needle. Okay, so these two forces are holding up the needle. And what this problem shows you is, Okay, so the surface will break and the needle will sink if this angle became 90 degrees. Okay. So the weight is being balanced by this. The weight is being balanced. The weight is being balanced by twice the tension times sine of this angle. This component of the tension is sine phi, and this component is canceling it. So the weight is being balanced by that. And the surface tension is, no, the tension, this tension force is the surface tension times the length of the needle. Anyway, so what this is showing you is for a needle that is 4 centimeters long, 4 centimeters is a little less than 2 inches. A needle that is 2 inches long, the maximum weight that can support is 0.6 gram, about half a gram. Okay, so that's what this problem shows you. Okay. Here are surface tensions. So for water at 20 degrees, the surface tension is that. Soapy water is 25. Okay, soap is a surfactant. What that does is, so if you put soap in water, so here's water molecules, okay? And now if you put soap molecules in water, what they do is soap reduces the force between water molecules, and that's how it reduces the surface tension, okay? And that's important because if the surface tension is too high, so in newborn babies, inner alveoli, it's like a rubber balloon. If it's too stiff in new babies, they're not able to breathe. They can't expand their alveoli. So some newborn babies lack the protein, a surfactant, to reduce the surface tension. So you need these proteins to make that balloon less stiff so you can breathe. Okay? Some of you might be aware of this problem. Okay? So surface tension is a property of the liquid. Okay, so anyway, surface tension. And again, you see as the temperature rises, the surface tension decreases. Okay. So when you want to clean something, if you want to wash something, what you want is the water to stick to that stuff and less to itself. Okay. So that's why if you use soapy water, the attractive force between water molecules is less, and if you increase the attractive force between the water molecules and the stuff, then you can clean away the stuff. Okay? And that's why if you heat water also, you're decreasing the force between the water molecules, and if the water molecule attracts the other stuff, dirty stuff, with a great force, then you can wash things away. Adding a surfactant such as soap reduces cohesive forces, which decreases the surface tension significantly. So this is of supreme importance in mammalian lungs. Surface tension also decreases with increasing temperature. This is the part of the reason why hot water cleans things better than cold water. Okay? All right, so now what we'll do is let's think of a soap bubble. So let's look at a soap bubble. Okay. So here's a soap bubble. There's surface tension. There's air underneath. Okay. So air inside. Okay. So what is happening is, so there's atmospheric pressure pushing you, and there's surface tension pushing you. So the air has to push back. So we'll cut this bubble into this half. This half of the bubble has to be pushed by the air inside. It has to balance the atmospheric pressure and this surface tension. So what that means is, if you have a bubble, if the pressure outside, this is atmospheric pressure, the pressure inside has to be greater than the outside pressure. Okay, so if you have a soap bubble, and that's because the surface tension is, this half of the bubble is being pulled that way, and so this higher pressure has to maintain that. All right, so for instance, when you blow a balloon, the pressure inside a balloon is greater than the outside pressure. Okay, so you need the greater pressure because the balloon is trying to, because of the surface tension of the balloon, this pressure has to be greater. And this is the formula for the amount of increased pressure. So this is the inside pressure minus outside pressure. For a bubble, it's 4 times the surface tension of the material divided by the radius of the balloon. Okay, so greater the radius, bigger the balloon, smaller the pressure difference. Okay, so smaller the pressure difference. So bigger the radius of the balloon, smaller the pressure difference. Okay. And for a drop, so for instance, if this was a drop, okay, a bubble has 2 surfaces. It has molecules on the top surface and the bottom surface. But if you have a liquid, then you have only molecules on the surface. Okay, so for a drop, the pressure difference is 2 gamma times R. All right, so again, greater the radius, smaller the pressure increase. Okay. So for instance, here's an experiment. So here's a big balloon and a small balloon. And if you attach them, what do you think will happen? Okay, so let me show you. Okay. So what I'm going to do is I'm going to show this to you. Here are 2 balloons, and they're attached. And right now the valve is closed. When I open the valve, what do you think will happen? Remember, the bigger the radius, the extra pressure is less in there than here. So the pressure is greater here, and this balloon will shrink and all the air will move here. Well, why do we care about this? Let me show you this first.
So I opened my Winn-Dixie Rewards app, and wow, savings just for me. Nice.
All right. So you saw that.
Hello.
So if you have 2 spheres connected, air will flow from here to there. Okay, well, why do we care about this? Well, you got to care about this because here are your alveoli. They're like little balloons that are connected. And if one alveoli gets bigger, what will happen? The air from a smaller alveoli will go into the bigger alveoli. All the smaller alveoli will collapse. You have 500 million of those. How the heck are you going to make sure that every alveoli is the same size? How do you solve this problem? Okay, so here's how the body solves the problem. Okay, if the balloon is bigger, you make it stiffer. Okay, and if the balloon is smaller, you make it weaker. Okay. So how does the body do that? How do you make it stiffer? Okay, so what you do is you put a surfactant in the water. Your alveoli is in the walls of the alveoli, you put surfactant. So think of the alveoli wall as water, and you put surfactant, and the surface tension decreases. So you have put so much surfactant, and when the volume gets larger, the density of surfactant is less, and it has become water, and it becomes stiffer. When the area is small, the density of surfactant is large, and so the balloon is softer. Okay, so that's how you prevent from the alveoli to, for one alveoli to collapse if the sizes are different. Okay. All right, so here's the extra pressure. Okay. And by the way, so for a drop, so you can think of, so now we'll talk about an air drop. So in water, these are air drops. Okay. And what we'll do is calculate the extra pressure inside these air drops. Okay. So the gauge pressure for air bubbles in 20 Celsius degree water. Okay, so for 20 degrees Celsius water, the surface tension is 73. Okay, so that's what you'll be using. Water is approximately, okay, so the extra pressure in this bubble for these size bubbles, 1 centimeter bubble, 100 micrometer bubble, and 1 micrometer bubble. Okay, 100 centimeters, 1 centimeter is that big. That's a large bubble. 100 micrometer is 1 micrometer is roughly the size of a cell. Okay. The pressure is 30 pascal, 300 pascal, and 300,000 pascal for a small bubble. For a tiny bubble, the pressure inside air that's 3 atmospheres. That's an enormous pressure. Okay. So to be a small bubble is not easy. Okay. But the last is a very large difference, 3 atmospheres between the inside and the outside of the bubble. Okay, for a bubble that size. All right. So we will talk about. Okay, so let me tell you how breathing works. Let's figure out how breathing works. Something that we do every day. Okay. So here are your lungs. Air comes through there, and then this pipe branches into tinier and tinier branches. Eventually, you get to alveoli. Okay. Why do we have to have this kind of structure? Because why do we have to have this kind of structure? Because what's your goal? Well, so you want to exchange oxygen with the blood in the capillaries, okay? And that happens via diffusion, and diffusion you can only go small distances in diffusion. So you have to fill air into tiny sacs, surround these sacs with blood vessels, and that's how diffusion can happen. Okay, so that's why you do this. Okay, now this is a tiny balloon. Okay, and this is surrounded by interstitial fluid. It's your alveoli are bathed in a fluid. Okay, so the extra pressure, it's like a drop. Okay, so the extra pressure is 2 times gamma. Gamma is the surface tension of this alveoli divided by the radius. Okay, so the extra pressure is that, and we'll give you the numbers on these. So smaller the radius, greater the extra pressure. So as your radius is changing, you remember you're changing gamma. That's how the body solves problems. So smaller the radius, the surfactant density increases and gamma decreases. Okay, so All right. So some of the problems one can encounter during breathing are if the surface tension of, if there was no surfactant in your alveoli, the surface tension of water is large, and you would need a lot of effort to blow these, to bring in air in the alveoli. Okay, so so it's like blowing a stiff balloon. Okay, you don't want this balloon to be too stiff. And if during exhalation, a reduction in the number of molecules, during exhalation, as air goes out, there's less air in there, and so you don't want the alveoli to collapse. Okay? And how do you prevent it from collapsing? You reduce the surface tension of the alveoli wall. Okay? So again, if one alveoli becomes larger than the other, you don't want that alveoli to keep blowing up. You don't want air moving from a smaller alveoli to the bigger alveoli. Okay, so, and again, it's balanced by surface tension. So you don't want one alveolus to inflate more at the expense of the other. Okay. So these problems are avoided in healthy lungs by pulmonary surfactant, a lipid protein complex that is absorbed into the air-water interface of the surface of the alveoli. So it's a lipid protein that is a surfactant that reduces the surface tension of the alveolus. Okay, and some babies don't have this lipid protein. Okay, premature infants often lack sufficient pulmonary surfactant to breathe on their own, a condition known as neonatal respiratory distress syndrome. It can be treated by introducing an artificial surfactant directly into the lungs. So they breathe this surfactant, and that goes into all the alveoli, and that's how they. And then as the baby grows, they are producing these lipid proteins, and so they fix the problem themselves. Yeah? So the surfactant lowers the surface tension of a liquid by reducing the cohesive forces. Okay. So again, so these are the water molecules. A surfactant will reduce the force between these molecules, okay, the cohesive force. When an alveolus expands, the increasing surface area dilutes the surfactant. So there's so much surfactant per alveolus, and as it gets bigger, the surfactant is diluted, and then there's less influence. Consequently, surface tension increases as the alveolus expands. So as the alveolus expands, the balloon is getting stiffer, so you don't have runaway expansion. And as the alveolus shrinks, the surfactant concentration is increasing, and it's becoming softer. The balloon is getting softer, so it doesn't collapse. Okay. So that's a built-in mechanism for avoiding trouble. Okay. When alveoli contract during exhalation, the surfactant becomes more concentrated, decreasing the surface tension, preventing alveolar collapse. Okay. I'm going to point some numbers, and okay, so this will calculate the excess pressure in millimeters of mercury for water bubbles this size. So 2 times 10 to the minus 2 centimeters. So 2 times 10 to the minus 2 centimeters. 10 to the minus 1 centimeter is a millimeter, so 2 times 10 minus 1 millimeter equal to 0.2 millimeter. Okay, the reason we are doing this is the size of your alveoli. Okay? So we are doing numbers for your alveoli. Okay, so a water bubble of radius that. Okay, so here is the water bubble. The pressure is okay, so here the water bubble, and surface tension for water is So the radius is that, and so this is the surface tension, and this is converted to millimeters of mercury. So for A, there it is 11 millimeters of mercury. A water bubble 5 times larger. So if the water bubble is 5 times larger, so the pressure inside, larger the bubble, smaller the pressure. Okay. A water bubble the same size as the alveoli with a surfactant. Okay, so this is without the surfactant, and this is the pressure with the surfactant. Okay, for this size bubble. You see the surfactant reduces the pressure inside the alveolus. Okay, and this will be important. We'll come back to that number in a second. Okay. The bubble in this example are similar in size to your alveoli. In the first case, the pressure inside is a bit high for easy inflation. So if you had no surfactant, the pressure inside is that high, and it's harder to inflate the alveolus. Your pressure would need to be greater than that to inflate the alveolus. So you can't breathe, okay? And that's what happens in preemie babies. Whereas in the second, it's a bit lower, causing the exhalation to be hard, okay? The third, this is just the right pressure, okay? So this is too small, okay? So we'll come to breathing, okay. So here's an alveolus. So here's the alveolus. Okay, for a fluid to move, the pressure here has to be higher than pressure here. Okay, so for a fluid to move in this direction, fluid moves from higher pressure to lower pressure. So when you want to breathe air, what is the pressure outside? What's the pressure outside? 1 atmosphere. Is this pressure changing? The outside pressure? No, it's not. So this pressure is constant, okay? So here's the pressure outside your lung, which is 1 atmosphere. If you want air to move from here to there into your alveolus, what do you have to do? When you breathe in, you have to reduce the pressure here. So what you're doing is you're changing the pressure inside the alveolus. And when you want to breathe out, you have to increase the pressure here so the air moves out. Okay? So you guys understand? So the pressure outside, the atmospheric pressure is not changing. So to breathe in, you have to somehow figure out a way to reduce the pressure inside your alveolus. And when you breathe out, you have to increase the pressure inside the alveolus for the air to move out. All right? So we just saw that the alveolus is like a balloon, and because this balloon it has tension in it, it increases the pressure by 5 millimeters of mercury above atmospheric pressure. So this is because of the balloon, it increased the pressure by 5 millimeters of mercury. So the pressure inside is greater than that pressure by 5 millimeters of mercury. How the heck are you going to breathe? The pressure is greater here. You guys understand the problem? Okay, so that's why you have a cavity, this cavity, there's negative, the pressure here, there's partial vacuum. This pressure is about minus 4 millimeters of mercury less than atmospheric pressure. Okay, so in this business, what we'll do is we talk about gauge pressure. So the gauge pressure is the actual pressure minus atmospheric pressure. So the gauge pressure outside is atmospheric pressure minus that. So the gauge pressure outside is 0 millimeters of mercury. Okay. And the gauge pressure in this cavity, this is the pleural cavity, intrapleural pressure. So this is the pleural cavity in there. The pressure is, the gauge pressure is minus 4 millimeters of mercury. All right, so in your alveolus, the pressure is 5 millimeters of mercury. Surrounding it is minus 4 millimeters of mercury. What you want is this pressure to go below zero for air to move in. So this is still not enough. 5 minus 4 is still plus 1. This pressure is still higher than that pressure. So when you breathe in, what you do is you lower your diaphragm, you expand your ribs, you make this cavity bigger, and the pressure drops. And when you expand your cavity, the pressure drops to minus 6 millimeters of mercury, and 5 minus 6 is minus 1 millimeter. And then air can move in. Okay? And so, during inspiration, now the pressure inside the alveoli is minus 1 millimeters of mercury. Air can move in. And when you want to breathe out, what do? You raise your diaphragm back up. The rib cage collapse. The rib cage relaxes. This pressure goes down. This pressure goes down to minus 4 millimeter, or it goes down to minus 3 millimeters. And 5 minus 3 is plus 2. Now the pressure inside the alveolus is greater than the outside pressure, and this air will move out. Okay? The pressure is plus 1 millimeter, and the air will move out. Okay. All right. So we talked a lot. So let me do this again. So here's the bronchioles and all those tubes. Here's the alveolus. Here's the atmospheric pressure. Atmospheric pressure, the gauge pressure is 0 millimeters of mercury. Okay. Gauge pressure is actual pressure minus atmospheric pressure, so that's 0 millimeter of mercury. This is not changing. So if you want air to move in here, the gauge pressure needs to be negative here. And when you want to breathe out, this needs to be positive. Okay? So inside the alveolus, when you're breathing in, it's minus 1 millimeter of mercury. That's what this is saying. And when you're breathing out, it's plus 1 millimeter of mercury. Okay? So what you're doing is changing the pressure inside your alveolus. And how do you change the pressure inside your alveolus? Okay, so this is the pleural cavity. You're changing the pressure here. Okay, so this is partial vacuum. Okay. And by lowering your diaphragm, you're changing the pressure here. By changing the volume of this, you're changing this. So you might have heard of the following. So in an accident, let's say this cavity gets punctured. What will happen? If it gets punctured, air moves in, that becomes atmospheric pressure. Now you can't breathe, your lungs collapse. Here's a collapsed lung. Okay? So how do you fix that? To be able to breathe, you have to have a vacuum. So you attach a vacuum pump. Okay? Until it gets fixed. All right, so air is suctioned out of an intrathoracic region to remedy severe pneumothorax. Although the body can slowly absorb the air. Any injury that allows air into the chest cavity increases the pressure to atmospheric pressure and forces lung to collapse due to the surface tension. This condition is called pneumothorax. It can be caused by an accident or surgery, or may occur spontaneously too. Okay. Okay, so for breathing, again, surface tension was important. Okay, and remember, so for breathing, remember what is it that you're doing? So the pressure outside is not changing, which is 0 millimeter of gauge pressure. The surface tension on the alveoli caused about 5 millimeters of excess pressure. And so you had to have negative pressure surrounding here. And this negative pressure, when you're breathing in, this negative pressure goes to minus 6 millimeters of mercury. Okay, minus 6 millimeters of mercury. So -6 plus 5 is -1, and air will move in. And when you're breathing out, this negative pressure goes to -3. 5 minus 3 is 2 millimeters, and that pushes the air out. All right, so that is how breathing happens. So it's something that we do all the time, and we take it for granted. And so but it's a complex process. Okay. I know I skipped over some slide. I didn't go in detail, but I gave you the punchline, and I didn't want you to be confused. So go ahead and read those slides, okay, and hopefully you'll understand it. All right. So we'll